Hi, welcome to this presentation for the term project, and I would like to start off with the problem statement that we have. And the problem statement is that we need to design and implement an M-point moving average filter to smooth out the higher frequency noises in an ECG signal. So we need to do it for different values of M, and the given sampling rate is 360 Hz. Now we know that a moving average filter is one of the most common filters used in DSP whenever we need low pass filtering and some sort of averaging. We would use moving averages, and we know that it's an FIR filter, so it's always stable. So let's start off with the difference equation. So it has a very simple difference equation. So it's basically the sum of the inputs being delayed, and they're actually divided by m, so it's sort of like a weighted sum. So the m here in the subscript denotes that it's an m-point moving average. So basically we're taking m points, and for a single value of the output we're taking the average of m points. So that's what the difference equation denotes. Now we can also write the impulse response using the difference equation. We just need to replace the input by a delta function, which we can do. So we can write the impulse response like this, which is very trivial. And now let's look at the impulse response. So the impulse response actually looks like a box in the time domain because of the the m number of delta function, delta in the time domain. Now there are many ways to find the output of a moving average. So we can use filter, we can like calculate the transfer function, take z transform of the difference equation that we had, and go like that. But what we are going to do in this part is I'm just going to use the difference equation that we have and try to find the output. So this is the difference equation that we have. Now we can for example, we need to find the output for m equals 10. We're trying to take 10 points at a time. So for that we can write the same equation like this, just replace them with 10. So this is the equation. So the implementation part we can do like this. So in program what we have done is we have two loops, and one for the sample itself, that is n, and the other one is for the value of k, that is the number of points that we're actually taking. So we're writing y of I equals y of I plus x of I minus j. So we're actually summing all those m points at a single I. So that is a summing action, and we'll also divide by m after that. So this is the programming logic that we have used. It's only the difference equation. So let's get ahead. Yes, so this is the input that we have. This is an ECG signal with added noise. So we can actually see that there are those fast wiggles in the signal that are the noise. So we need to somehow remove that. So we're using MA filters for that. And if we take a DFT of this input signal, we'll find that there is one component of higher frequency that is somewhere around 50 Hz. That is the noise. So we will come back to this figure once again once we have filtered it. Now we will first do for 10-point moving average. So for that, this is the output that we get. We can see that the plot on the top is the noisy signal, the original signal, and the one on the bottom is the filtered signal. And we can actually see that those wiggles in the noisy signal are now not there. So it has reduced. So as we increase the value of m, we can see that it has reduced further, and those spikes have come down. So basically the rate at which this signal is changing has slowed down. And we further increase the value of m, we see those curve getting smoothened out. And for m equals 100, we can see that now the curves are even more smoother, and they have sort of shifted to the right. we'll see that why is that the case. Okay, now in this part what I've done is I have overlaid the signals just so that we can see the delay and how it's averaging out. So we can see that as I increase the value of m, we see a trend in the output. So obviously the curve is getting smoothened out with increasing values of m, and for 100, m equals 100, we can also see the delay part. So we can see that it has started to deviate from the original signal. So that delay is what we're concerned with. So this is the DFT spectrum of the signal after the filter. So we'll go back to the original DFT which we had just seen, thus here. So in this graph we can see that there is a frequency of 50 Hertz, but if we see the filtered output, there is no component around 50 Hertz. But also one thing to note here is that there is some attenuation in the region that we did not want. So that is the drawback of a moving average. So we don't have a very precise control over the cutoff frequency. Yeah, so we have seen that how high frequency noises have been attenuated completely using a moving average filter, but also there is a drawback that it actually attenuates some of the signals that we really want in the signal. So some unwanted and some wanted signal also get attenuated. Okay, yeah, we can see that with increasing values of m, the delay was also increasing. So the delay is actually proportional to m, and it's m minus 1 by 2. And we can also see that moving average is actually acting as a low pass filter with decreasing cutoff frequency as we increase the value of m. So there are a lot of applications for moving average filter. So one of the applications is a technical analysis tool in stock market to average out the prices of the stocks for a given number of days. And to filter high frequency noises, we have seen that while making different sort of measurements, there are some sort of noise signals that come in. So if we need to filter that out, so we can use a moving average filter. So if we ever need some sort of averaging action, we can use moving averages. And if we need smoothing, if we need to smoothen some curves, so we can use the moving average filter. Now moving on, I would like to go to the GUI for this m point average. So this is the GUI. So we can see that the slider is actually for varying the values of m. So as we vary the value of m, we can see this plot is for the output of the moving average filter. And as we increase the value of m, we can see that the curve has started to smooth out. So if I just increase it to 100, we can see, yeah, it's already smoothened out now. So that was the GUI part. And this is the source code which I have written. So one more thing I would like to focus on is that we can see if so this is the magnitude response of the MA filter for m equal to 100. So we can see that the frequency here we can see that around the DC, that is zero frequency, we have a good response of the filter, but as it's deviating from that, as it goes away from that frequency, the attenuation, the gain is almost getting to zero. So we can see that it's sort of acting like a low pass filter. And this is the source code for getting the output of the moving average filter. We have discussed this the rationale or the logic behind finding the output of the moving average, and we have also verified it with filter function in MATLAB. Thank you. That's it, and thank you.